let me share my screen. Let me add here that I'm going to email a new Zoom invite for each class. So that code that we have will no longer work. With respect to the test, there is one question that I would like to go over. I have to apologize. The big survey question with the 3 loops, when I was picking out the question in the test bank that I had, there were 3 options, and I chose that one based solely on the fact that the numbers weren't as large. And so I thought that just conceptually that would be easier for everybody. And I should have looked at it in greater detail because the information that was presented was different than all of the examples that we had done in class. And so if you drew a Venn diagram and started labeling it correctly with numbers, I gave you half credit. But because that question was of a totally different degree of difficulty than anything that we did in class, I am going to go through and give everybody full credit. The easiest way for me to do that is through the MyLabs gradebook. So I'm gonna just, give everybody credit for the questions so that if you didn't do it because it was too difficult, you'll get credit. If you did attempt it, or if you, you'll get some extra credit. If you got it right, you'll get a little bit more extra credit. I apologize for that. I should have been more conscientious when I picked that question, but not realize that there were any at all in the textbook that were not presented in the same way. I do want to go over that question, and if you have questions on them, a couple other, but there are a very small number of people who did not yet take the test, or if they did take the test, their work did not come to me. And so I just want to connect with those people before I go over it. So if you fit into that category, let's not talk about it now in front of everybody, but if you could stick around for a minute after class, I'll discuss it with you. But who had a question?
Yeah, I didn't have enough time to finish the test. It ran out of time.
You know what? It was a 75-minute test. That's full class time. That is what I would have given for the on-campus test. Basically, I used to let people have extra time to finish a test, and I got scolded by the accessibility office. We're only supposed to give extra time to people if they had the paper.
There was a question that I didn't understand.
Well, when next class, we'll go over whatever questions you have questions on. Okay.
Okay.
Right. Anybody else have anything that they want to talk about before we get started today?
I ran into a similar problem with running out of time. Out of the questions I did do, I only got 2 wrong. But I know it wasn't the fact that like my grade was bad because I didn't know what we were doing. It was that the fact that I didn't have enough time to write down my work.
Again, no, in terms of extra time, we're only supposed to give it to folks who have the accessibility office. And in terms of showing your work, you don't need to rewrite the question. I mean, the questions are in front of me. You just need to put down what work you do to get your answer. And if it were a pencil and paper test, I mean, that was what you would have to do anyways. So, but
I'm sorry. Could I interrupt for a second?
Sure.
I had a question for Michaela.
Yeah.
Michaela, you there? Can you hear me?
Yeah.
Were you trying to do the work for every question or just some of them?
Yeah, I did the work for most of the questions. There was like a couple that I didn't think I needed to, but like I wasn't sure if she wanted the work for every question or not. So I
Yeah.
actually did the work for every question.
I was gonna point that out. I only did the work for maybe 6 questions, and it didn't seem as though our professor wanted us to show the work for even most of them. We didn't really
You
need
know
to.
what? No, I did want to see the work for most of the questions. I
Oh, you
want
did?
whatever work that you needed to do to get the answer.
Okay, yes.
A
Okay.
lot of them, in terms of showing your work, you could have drawn a Venn diagram, or for example, if it was one of those compound set things, and you were looking for something like A intersect B complement, the type of work I would be looking for is write down what's in A intersect B and then write down what's in the complement. I wasn't looking for, rewriting the question, just what you would, hopefully you've been putting some work down, pencil and paper when you do the homework. The amount of work that you would do for something like, the homework question. I mean, that was, and it's what I would expect on a pencil and paper test.
Right. I understand. I was just calculating, if I remembered correctly, about 2.25 minutes for every question. And I thought if I were to meticulously show the work for every single question, I might have been tight on time, especially for that one question that you wanted to go over next class, the one with the Venn diagram.
I will,
Yeah.
I will give everybody credit for that. And then two, just test taking skills. If something's not coming to you, skip that question and go back.
Exactly. I had to. It took me like 10 minutes and I still got it wrong. I was ripping my hair out over that one. But thank you very much for giving us credit for that. That's very generous of you.
No, I thought I had chosen a different problem. So I didn't realize the information that was given with to that problem was different. But Michaela, well, let's talk after class, okay, hon?
Okay.
All right.
But that's how I felt like Michaela. I felt like I was focusing more on the time running out than the actual like questions.
Would you rather not have the clock telling you how much time you have left at the top of the page?
I don't know though. It kind of helps, but I guess it gives you kind of an anxiety, like to hurry and do the stuff.
Yeah. Well, I'll tell you what, think about it and let me know your preference before the next test, and I can change settings accordingly. I did also have the test set up so that the questions were randomized. They weren't all in the same order. Would you prefer if I did not randomize them and put the quicker questions at the beginning and the longer questions at the end?
Yeah.
Okay. So I will try to remember to do that next test also. All right?
Thank you.
Okay. So we're totally changing gears today. Yay. We're going to start looking at probability, and we're going to start looking at today something that's called the fundamental counting principle. And we're going to see that counting is important in probability. In order to find the probability of something. P-R-O-B, I started talking in the middle of that word and now I can't spell it. P-R-O-B-A-B-I-L-I-T-Y. And so let's look at an example of a type of question where you might see on this first homework where you have to count. Let's say that Susie Q is picking an outfit. Each outfit consists of one sweater and one pair of jeans. No layered look. She's only going to wear one of each. She has, let's say, 4 sweaters. And let's say she has 3 pairs of jeans. I want to know how many outfits are possible. So I'm open to suggestions.
We could use the fundamental counting principle to conclude that there are 12 unique combinations.
And tell me, arithmetic-wise, how you came up with that 12.
Okay, well, the principle tells us that if we have 2 groups of items and we can select 1 item from each group, then the number of unique combinations is equal to the number of possible items in every group multiplied together. So we have 4 times 3, which is 12.
Yeah. I'm just looking for the word multiply. 4 times 3 equals 12.
I'm sorry, that was over.
No, that's okay. We're going to actually write a summarization, a similar summarization of those words in a minute.
Okay.
A diagram to show why.
I think Robert has a future as a teacher.
Yeah.
Right. I was thinking to myself, like, who is this?
First, she can pick a sweater. And so, and folks, this is why I teach math and not art. These are sweaters. And they're different. Each one has a number on it. 1, 2, 3, 4. She's got 4 sweaters. And then if she wears sweater 1, she can pair it with any one of the 3 pairs of pants that she has. If she picks sweater 2, she can pair it with any one of the 3 sweaters that she has. I'm sorry, any one of the 3 jeans that she has. I apologize. If she picks sweater 3, she can pair it with any one of the 3 pairs of pants that she has. And if she picks sweater 4, she can pair it with any one of the 3 pairs of pants she has. And so if you look at each of the possible sweater pant combination, there's 3 for each sweater, and so we multiply. And no, I won't make you draw that tree diagram, but for people who are questioning why you multiply, does that help? So the fundamental counting principle says that if one event can occur m ways, where m is a variable, and another can occur n ways, where n is a variable, then the combination of events can occur m times n ways.
Oh, what does that M stand for again?
It's a variable, it's just a number.
Okay.
So for example, she could pick a sweater 4 ways. So m would be 4 there. And n would be another variable, another number. She can pick a pair of pants n ways. So the combination can occur m times n ways. And so if you know how many ways one thing can happen and how many ways another thing can happen, the two can, with a combination of events, can occur m times n ways. We multiply. And you're going to find that I think usually in this course, I think this homework on the fundamental counting principle becomes one of the least challenging for people, because the rule of the day is, in most cases, we multiply. We'll look at a couple of examples, though, where the multiplication gets a little bit more involved. But let's start with some pretty straightforward examples. Let's say we go to a restaurant. It's a particular restaurant. All they offer are grilled cheese sandwiches. You can pick one of, let's say, 4 types of bread. So 4 types of bread. We could say there's like white bread, wheat bread, rye bread, and pumpernickel, something like that. And let's say you can pick one of 5 types of cheese. So, I don't know, cream cheese, American cheese, cheddar cheese, Swiss cheese, mozzarella.
Mm.
So how many sandwiches are possible?
20.
Who said 20?
Me.
Zach, tell me how you got it, because that's a perfect answer.
Yeah.
Did you multiply 4 times 5 gives us 20?
Yeah. You got 4 breads and 5 different cheeses for each.
And I have to apologize. Maybe I should have had a handout for these with these word problems. I think it's the setting up the situation takes much longer than the work. Is everybody comfortable with that?
Oh, this is fine.
So going back to the definition you gave us earlier about the fundamental accounting. So like, would the types of bread be M and the cheese be N?
Yep.
Okay, I just wanted to make sure I understood.
Yep. And we multiply it. Spot on. You got it. And so here the events are picking your bread out and picking your cheese out.
Okay.
Okay. Let's look at a slightly more involved example. This time, let's say we're trying to make a schedule for spring. Let's say that you and your advisor says you're going to take 4 classes. And based on your program, you're going to be able to pick one from each of the following categories. And so let's say that there are 3 possible math classes that you can take. Let's say there are 2 possibilities for science. Let's say there are 4 possibilities for English. And let's say there are 2 possible psych classes. How many schedules, different schedules can you make?
$48.
Wow, you're fast. How are you getting the 48?
Multiplied all the numbers together.
And so is everybody all right? The counting principle, specifically the way we have it written, spells out if we're looking at 2 events, one after the other. If there's more than 2 events, it just means we're going to multiply more than 2 numbers. And so that will give me 48 schedules.
I'm just fast at multiplying. I'm really good at it.
Good. And so if your categories are spelled out clearly and the options in each are spelled out clearly, it's that straightforward. Are we comfortable with this so far, folks?
I actually like this better than the last stuff. Kind of easier to me.
Yeah, you know what? We start with sets because this course was written to prepare people for statistics class, and the statistics instructors ask that we cover the sets. I like to start with it because I think pretty much everything else we're doing between the probability, the statistics, and some of the consumer finance, I think it's probably similar to something that you've seen in a math class before, maybe in high school. Maybe the degree of difficulty is ratcheted up a little bit, but the topics are familiar. And I think that they're mostly computational. What I like about the sets is it's much more reasoning and thinking and theoretical. And most upper level math is much more reasoning and thinking and theoretical. But I also thought it might be more fun if we start this semester with something you haven't seen before, as opposed to like that, like, oh God, I've done this, you know, kind of like a doldrums type of thing. So I don't know. Choice on my part. I apologize if you guys didn't agree with it. But next example is similar yet different. This example, we're going to have a true false quiz. Is everybody all right if you're taking a true-false test or a true-false quiz? You shouldn't ever leave something blank. If you leave it blank, you're not going to get any credit. If you take a guess, you got a 50-50 shot. So we're not going to have leaving it blank as an option. If there are 6 questions, how many ways can we answer it? And this one's a little bit different than you might originally think. And I mean, if we're just guessing, you know, it's totally random. We didn't study at all. We're just guessing.
36.
You
Wouldn't it be 12? Because
neither.
Can we raise 2 to the 6th power?
That's what we're going to have to do is we're going to have to raise 2 to the 6th power. If you think about it, how many decisions are we making? Isn't each test question a separate decision? Right? We've got 6 questions to answer. So we're making 6 decisions. So like in the last question where we were picking 4 courses, here instead of 4 courses, it's 6 questions. And for each question, how many choices do we have? 2. There's 2 possible answers for this question, 2 for this, 2 for this, 2 for this, 2 for this, 2 for this. And the counting principle says we take the number of choices we have for each thing and multiply. That will give us 2 to the 6th. And when you multiply that out, let's see, 2 times 2, 4, 8, 6, 32, 64. And so what you have to say is, you know, well, we could think of each test question as a separate event. We've got 6 events, and each of those events have 2 possibilities, which leads us to multiply together 2 by itself 6 times. That one, all right.
I was doing it one time, that's why.
Yeah, and I usually in class on campus, I ask people, and most people with this question think, you know, of that idea of multiplying and getting 12. The fact that you took 6 to the 2nd, you know, it's, well, yeah, we're going to be using exponents, but flip it around a little bit. It's 2 to the 6th. 6 times we're doing 2 choices. And so another similar example, let's say it's multiple choice. Let's say that each question, oh Lord, let's try that again. Each question has 4 choices. Let's say there are 10 questions. And again, we're not leaving anything blank. How many ways can we answer?
Uh, 40.
I don't think it's 40. Let's look at this quiz for a minute.
Okay.
Can we think of each question as a separate event? Each question is a separate choice we have to make? How many questions are there?
10 questions.
10. 1, 2, 3, 4, 5, 6, 7.
I was doing it the other way.
Yeah.
Or
And for each question, there are 4 options. And the counting principle tells me that to find the number of ways I can pick for each, I multiply. And so that actually gives us 4 to the 10ths, which is, how are you folks at exponentiation? Does everybody know how to do that with your personal calculator?
yeah.
Carried arrow, right?
So with Texas Instruments basic calculator, you would type that in as 4 caret up 10, which gives you a lot of ways. Yes? Anybody want to tell me what you're getting?
1,048,576.
1,048,576. How cool is that? And that would be like how many different ways you could just guess at each of them. Like if I went in and took Spanish multiple choice. I've never taken Spanish in my life. I would be clueless. And so, you know, it would be that many different possible ways of guessing. Of all those ways of guessing, how many would get every question right? To get every question right, wouldn't there only be one way of doing it? Because there's only one right answer for each.
I did it backwards.
Oh, you did 10 to the 4th instead of 4 to the 10th?
No, I was doing 4 questions and 10 choices. I was thinking
Right.
like 4 times 10.
No, it's and each choice is a separate event, so you have to have something that you multiply for each of them. And this idea of counting for things like a test or quiz can also be used for something like if we look at a phone number. Is everybody right? A phone number has a 3-digit area code. And a 7-digit number. And has anybody ever noticed neither the area code or the number ever starts with, either of them can start with 0 or 1? Did anybody ever notice that phone numbers never have 0 as its first digit? And that's because back in ancient times, if you dialed 0, you got the operator. And so if you start with a 0, it immediately would connect you to the operator. I don't know if that still happens anymore. And then they never start with 1, because when you type that 1 in, it gets you a long distance, right? If you're not using a cell phone, if you're using a landline phone for long distance, you have to dial that 1 first. And so neither the area code nor the phone number start with a 0 or a 1. So I'm wondering how many phone numbers are possible?
0.4 billion?
There's a lot of them. Should we go through the process that we've been developing to see how many?
Sure. Sorry, I wasn't sure if you wanted us to give you the answer.
Well, it's not quite 4 billion.
It's not, I said 6.4 billion.
Okay, 6.4 billion.
Yeah.
Yes, didn't hear the 6, I heard the 4.
Sorry.
Okay, so 3 choices for a number for the area code, 10 choices for the number for the phone number. How many digits are there to pick from?
Well, if we start with the first group, which is the first digit of the area code, we have 8 choices.
Okay, but just in general, is everybody familiar with 10 digits? You can have 0 through 9, but
Yeah.
because we can't have 0 or 1, you're right, the area code only has 8 choices. And then the phone number itself only has 8 choices. Okay, go on, you're doing a great job explaining.
Okay, yeah, sure. Well, since we've defined the first and fourth groups, every other group has 10 choices. And then we just multiply them all together, right?
And is everybody comfortable with why there are 10 choices for all of the others and 8 choices for those 2 spots? Any questions?
A little
Yeah,
confused.
no, I missed that. I don't.
Okay, if you stop and think, for each possible number that you can dial every time you hit a number on your phone, aren't there 10 that you can pick from? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
Yeah. And so over here, for the very first one, if it can't be 0 or 1, that means all we have left is 2, 3, 4, 5, 6, 7, 8, 9, or because we're taking 2 possibilities out, there are
Oh, okay.
8 left. But then the next 2 digits can be anything. And then this one also cannot be 0 or 1. So there's only 8 choices, and then the rest can be anything. So there are 10 choices. A little bit better, hon?
Oh, I
Yeah,
get it.
thank you.
And so then 8 times 8 is 64. And then each of the 10s, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, would give us a 0. And so that gives us 6,400,000 different possible phone numbers. Does that look like enough phone numbers, do you think? I always wonder, because I know like some people have like multiple cell phones. It's like, wait, are we going to run out of phone numbers if everybody starts getting more than one phone?
So only because the first 2 can't start with 0, 1. That's why it's 8.
Yes.
And then the last one can start with 10.
Right.
Uh,
If you think, I'm sure you can think of a phone number where that, like, this is the area code, and then you've got 3 digits and then 4 more. I can think of a bunch of phone numbers where that digit could be a 0. Okay. Let's look at one more example like this. And this time, let's look at license plates. And I just want to look at license plates that are not vanity and that are not commercial. So we're looking at license plates on plain old cars. Anybody here have a car?
yes.
Yeah.
Yes.
Okay, think about your license plate. Isn't it 3 letters and 4 numbers? I'm going to shut up and ask you folks to take a minute and try to figure out how many are possible. And let's wait to give everybody a chance. And I hope nobody thinks that there's just 12 different license plates, because that would be tough. Oh, and just background knowledge. How many letters are there in the alphabet?
26.
26. And when you have something like a license plate, is it okay if a letter repeats? I think so.
Yes.
And is it okay if a number repeats?
Yes.
Yeah.
Yes. And it's okay to have a 0 in a license plate number, right?
Yes.
Yes. Okay. So keep all of that in mind as you set your problem up. Are we ready to go over, or do you guys want me to wait a minute?
Ready.
Ready? Okay, so for the first letter, we have 26 choices, and actually for each letter, we have 26 choices. And for each digit, we have 10 choices. That would give me 26 to the third times 10 to the fourth. And so what are you getting?
I messed up on the numbers one. Since we were including 0, I thought it would be like 11.
No, because if you think about it, 0 through 9, and I'm using my, I keep forgetting that when I'm showing you the board, you can't see me. I'm using my fingers to count. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 digits. In general, we work in a base 10 number system where the place values are all powers of 10. And so we do have 10 different digits. And actually, I think the reason we work in a base 10 number system is because people started counting on their hands and we got 10 fingers, right? That's right. We're in decimal world. At least that's what I've always thought. I could be wrong. But when you multiply that out, what are you getting, folks?
175 million.
Yep, the 75, you're right, and I'm remembering wrong as I write it. 175 million. 760,000. So, interesting.
I have a question.
Sure.
What if you had a license plate that didn't have numbers?
If you had a plate that was all letters, there'd probably be a lot more possibilities because we'd be, like if all 7 could be letters, it would be 26 to 7th, which would be a huge number.
I saw a license plate yesterday that said "Marry Me."
Yeah, well, those are your vanity plates. And so we were excluding vanity plates. I mean, I've seen all sorts of license plates where people have like their name on it or all sorts of weird things. I'm just looking for the
Just
number of
regular.
license plates with like people who don't really care what their license plate says and they want to spend the least amount of money at that DMV. You just get that standard plate. So I guess in some states, in addition to all of these possibilities, they have like different pictures that you can pick, right? And so that would be another set of options that you have. But this fundamental counting principle, figuring out how many decisions you're making, figuring out how many choices you have for each, and then multiplying. Is everybody comfortable with that idea?
Yeah.
If so, we're going to look at one particular application of the counting principle, and it is something that's called permutation. And so if I look at permutations, my desk is too full. I'm trying to rearrange things. Permutations. Permutations are arrangements of, there are 3 criteria that we have to have in order to make something a permutation. We have to have distinct objects. And by distinct objects, I mean each object is different. We can't repeat the same object twice. Each object can only be chosen once. And if something's a permutation, order matters. So, real basic example of a permutation. Is everybody ready, or do you want me to wait a minute?
Just one moment.
Okay.
One moment.
And repeat. Order matters.
Right.
All right.
So let's look at an example. Let's say how many ways can I put 4 people in a line? Before we start looking at how to figure this out, is everybody all right that this fits that criteria? 4 people, they would each be different. If I'm putting them in a line, lining them up for something, no person can take, no one of them is going to take up 2 spots in the line, right? That person can't be repeated. They can't be used twice. And if I'm looking at how many different ways I can arrange them, order would matter. Do I want to go from tallest to shortest? Do I want to go from shortest to tallest? Do I want to put them alphabetical by first name, alphabetical by last name? You know, think about, you know, something like a police lineup and the amount of thought that usually goes into the order in which those people are arranged. So does it make sense that for each spot in the line, I'm making a choice who goes there? If I have 4 people to pick from, how many choices do I have for that first spot? 4. But now one person's in line already. So how many choices do I have left for that second spot?
3.
3. And now 2 people are in line already. How many choices do I have left for that next spot? 2. And then finally, there's just 1 person left for that last one. And again, because each time we pick a person, we're making a separate decision. It's considered like a separate event. The counting principle tells me to multiply those, and that gives me 24 ways. For example, how many, let's say 3-letter passcodes can I make from, let's say the letters A, B, C, if there's no repeats? Picking a 3-letter passcode. So I have 3 decisions to make. What letter comes first? What letter comes second? What letter comes third? The letters are different, A, B, C, and order matters. Okay, I like that 6. Do you want to tell me where you got it from?
So you have, it's a 3-letter passcode, so you have 3 slots, and you start with 3 letters.
Mm-hmm.
You already have 1 letter there. So the second slot, you only have 2 choices to pick from.
Beautiful.
And then for the third slot, you only have 1 letter left. And then you just multiply them.
I like it. And that gives us 6 ways. That idea of permutation, all right.
Yes.
Okay. Then, and I'm sitting and I'm cursing myself because I don't see the calculator that I want on the desk. I might have to run downstairs for a minute. This idea brings us to something that's called a factorial. factorial is the product of a natural number and all the natural numbers less than it. So if n is a natural number, let me know when you guys are ready.
I'm ready.
N factorial is written as n with an exclamation point after it. And that's my number times the number one less than it times the number one less than that. And I'm going to multiply all the way down to the last natural number is 1. So that's how we define a factorial. There is one exception to the rule. Zero is not a natural number, but we're going to define 0 factorial to just equal the number 1. So for example, if I see 5 factorial, 5 with an exclamation point, that's 5 times next number would be 4, then 3, then 2, then 1. And I'd need to multiply across. When you multiply that out, 5, 4, 3, 2, 1, what do you get?
$120.
Beautiful. Now, what if I ask for 6 factorial? That would be 6 times 5 times 4 times 3 times 2 times 1. And what does that give us?
720.
720. And the multiplication gets a little tedious, yes?
Yes.
So what if I asked you to do 11 factorial? Does anybody want to really write out 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and multiply them? Or for that matter, does anybody want to really type that 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 into a calculator? I don't think so. So the, I'll be right back, okay? I want to run get a calculator to show you. Stop screen sharing for a minute. Does anybody have this calculator?
Yes.
With this calculator, to find 11 factorial, what you're going to do is you're going to type in the number 11. And then as you look at the calculator, there is a button labeled PRB. PRB stands for probability. So we're going to press that probability button. And then as you look at the probability button, you see there's a bunch of choices. You're going to arrow over until the exclamation point is underlined. And if I hit enter, you see what I've got is exactly what I had written, 11 factorial. And so now if I hit enter again, and I'm going to share my screen again, 11 factorial from my calculator is giving me, what is that? 39916,800 or 39,916,800.
What if you don't have the probability number button?
If you, what calculator are you looking at?
I have a scientific calculator, just not the Texas Instrument.
If you have a scientific calculator that's not a Texas Instrument, who is this?
Zach.
Zach, do you want to hold your calculator up and let me look at it for a minute?
Yep.
And let me change to speaker view. If you look in the, oh shoot, I'm not real familiar with that. Is there an exclamation point in any, above any of the buttons in fine print? Is there like an N factorial?
Oh, yeah. There's an X with an exclamation point.
Okay, so type in your 11 and then press your second button. And then whatever button has that X with an exclamation point with it. Did it give it to you?
Yeah, but it gave me the wrong answer.
Okay, let me see what your display looks like, please.
When I press the one with the exclamation point, it shows a negative one.
Okay,
Wait, I got the same calculator. You're supposed to press shift. Wait.
Okay, thank you.
Press the shift button over, I don't know where it is. Over there. And then you press the X1. You see it? So
Yeah.
type the 11, then press
I got
shift.
it.
Yeah. All right.
Oh, thanks.
Thank you, Chris.
You're
One more question.
What kind of calculator are you using, Professor?
The first one that I showed was the Texas Instruments TI-30X. That's actually what I would recommend it. I think I had recommended at the beginning of the semester if you hadn't had a calculator yet. Is there anybody who has, this is an antique one, but is there anybody who has a graphing calculator? Does anybody want to know the button sequence that you need for a graphing calculator? No need? Okay. So with one calculator or another, could everybody get that answer?
Yep.
Yeah.
Okay, then let's look at a question. Let's say, how many orders, how many ways can I arrange the letters of the alphabet? Does it make sense that that would be the 26 times the 25 all the way down to 1, which would be 26 factorial? Before you do it, what type of number do you expect for 26 factorial?
A big number.
A big number. So let's go through and let's see exactly how big that number is. when I type enter on mine, I'm getting a decimal. I'm getting 4.032914611. But after the decimal, whatever calculator you have, is there something that says like times 10 to the 26? Or
Yeah.
sometimes you might have, instead of times 10 to the 26, some calculators might give you E26. What that's telling you is that your number is very large, much larger than your calculator display, and it's putting it into scientific notation. And so picture that 4.032914611, but multiplying that decimal point, moving that decimal point over 26 places. And so if you're expecting a very, very large answer and you get a decimal instead, look at the back side of your display. It might be throwing it into scientific notation, but then that also is, you know, sometimes using your calculator for some of these is not the most expedient way. Before we, before we start playing a little bit with arithmetic of permutations, I want to just add that there are n factorial permutations of n distinct objects. And again, that's no repeats, and order matters. And this is if we're using all the objects. Before we look a little bit more at different types of permutations, let's just look at a little bit of arithmetic with factorials. What if I have something like, let's say, 10 factorial divided by 8 factorial? You could go through and use your calculator to evaluate it, but is everybody all right if just for a minute I go a little old school on you? 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. And wouldn't the 8, 7, 6, 5, 4, 3, 2, 1 cancel each other out and leave me with just the 10 times 9 or 90? I believe there's some in the homework that if you were to use a calculator, let's look at something like 100 factorial over 98 factorial. With something like that, if you're putting a fraction in your calculator, you're going to put parentheses. But there's an awful lot of calculators that when you type something like that in, it says overload. Too big. Numbers are too big. I can't deal with them. Seeing the last example done out, if I'm multiplying 100 down to 1, multiplying 98 down to 1, and dividing, doesn't make sense that everything would divide out except the 100 and the 99. And so that would give me 9,900. And so you're going to find with some of the factorial questions on the homework, it's easier to actually do it in your head than grab that calculator. Does that example make sense?
I don't know.
No?
I don't know.
Okay. Let's look at it, doing it all out. 100 factorial would be 100 times 99 times 98 times 97, all the way down to 3, 2, 1. 98 factorial would be 98 times 97, all the way down to 3, 2, 1. With me so far?
Yes.
And think about now how you reduce fractions. You can divide out common factors. And so wouldn't everything divide out? Wouldn't everything match up except for the 100 times the 99?
Yes.
Better?
Yes.
Yes. And so if you've got one factorial over another factorial, if the number in the top is larger, you're only going to really be multiplying the factors up until whatever the number in the denominator is. To this point, we've looked at counting principle, we've looked at the definition of a factorial, and we've looked at permutations when we use up all of the objects. What we're going to look at now is permutations when you don't use all of the objects. And let's start with an example. Can I turn the page?
Yes.
So let's say we have a race. Let's say there are 10 runners. And we only worry about the winners. Think like the Olympics or something. We only want to know gold, silver, bronze. How many ways? Can they finish? And I don't want to worry about the finishing of all the runners, just first, second, third. So going back and trying to find this using our counting principle, we've got 3 places to fill. Going on the assumption that all runners are of equal ability, there are 10 people who could possibly cross the finish line first. But then after somebody crossed the finish line first, doesn't that give me 9 people left to cross the finish line second? And how many people would there be for that third spot?
8.
8. And what should I do with those 3 numbers?
Multiply them.
Beautiful. And so that gives us 720 ways. And there's another way of writing that. If I look at NPR, that's the number of permutations. And so remember, because it says permutations, we're thinking distinct objects. We're thinking none of them can repeat. And we're thinking order matters. So number of permutations of n objects if I want to pick R of them. Exception? Anything permutation 0 will always equal 1. And let's think about that for a minute. Anything permutation 0 always equals 1, because if I wanted to think of how many ways from class today can I pick on somebody and like really be mean to them and you know, choose somebody, be mean to them, and you know, make fun of them and throw them under the bus. And so hopefully from the 20 people here today, I wouldn't pick anybody, right? How many ways are there of picking nobody? There's only one way of picking nobody, and that's to pick nobody. And so anything choose 0, there's only one way of doing nothing, and that's to do nothing. And so if I look at that example that we just did, we had 10 runners and we wanted to pick 3 of them. And so 10p3 turned out to be 10 times 9 times 8, which turned out to be 720. Now there's 2 ways of looking at that 10p3. I lied. Yell at me. There are 3 ways of looking at finding that NP3. The way that I first learned in pre-calculator days is that the first number is the starting value, and the second number tells me how many factors. So in pre-calculator days, my first number was 10, and I wanted 3 numbers, and that would be 10p3. So for example, if I wanted, let's say, 6p2, using this definition, I'd start with 6, and I have 2 spots to fill in, so that would give me 30. The first number should always be, the second number should never be larger than the first number. First number should always be the larger of the 2 unless they're equal. Does it make sense if I had NPN, if I was picking all of them, that would just give me n factorial. And so this is the way when I try to figure out a permutation out of a calculator, this is how I do it. However, if you use help me solve this, another definition is that NPR is equal to n factorial over n minus r factorial. And I know that some people do go into use help me solve this. And so this is the definition that Mr. Blitzer uses. And I don't expect you to go through and do this level of work each time, but I don't want you to be confused if you use help me solve this and see it. So let's go back to that, what we just did, 10p3. Using this definition, that would be 10 factorial over the difference 10 minus 3 factorial. Is everybody all right with just the substitution side of things? So what's 10 minus 3?
7.
10 factorial over 7 factorial. And so that would be 10, 9, 8, 7, multiplying all the way down to 1, over 7 multiplying all the way down to 1. And you see, that gives me that same product that I had before, 10 times 9 times 8. And so it's another way of getting at that same product. 3 factors starting with 10. But I'm guessing that none of you want to work that hard to find something like 10p3. So the way that I'm thinking that most of you will want to do 10p3 is to take your handy dandy calculating machine, type in the number 10, and if you have this model, we're going to go over to that probability menu. And when I go over to that probability menu, I don't know if you guys can see my display or not. Do you see that one of the first option is NPR? So I'm going to press enter. I want that underlined NPR. And I'll go 10p, then I'll type the number 3. And then when I hit enter, I get that same 720 that I did by hand. Those of you who have that other calculator, if you look in fine print above all the buttons, is there one that says above one of the buttons NPR or XPY, something like that?
Yeah.
Yeah. So what you're going to, if you have that button, you're going to press first the 10, then you're going to press shift. I apologize before I said second instead of shift because that's what TI calls it, but you'll press shift.
Yeah.
Then you press that button and then put in your second number. And
oh yeah, I got it.
You got it?
Mm-hmm.
So is everybody getting it with their own calculator? So
Yep.
let's look at an example. Why is this not moving on me? I guess I'll make an extra page. Another example. Let's say class of, let's say, 22 students. How many ways can I pick 3 to do 3 different problems? And so let's say that those 3 problems are very different. Let's say one problem is just adding 2 numbers. One problem is a set question like what we did in the previous unit. And let's say one problem is a calculus problem. If you were one of the 3 people, would it make a difference to you whether you had to do a simple addition problem, a set problem, or a calculus problem? Would you care which problem you got?
No.
No? You wouldn't mind if I asked you to do a calculus problem in front of everybody? I'm thinking that because the problems are different, given a choice, I would probably rather do the addition problem. And then my second choice would be the sets. And then the last choice would be the calculus. Because they're different, order matters. So this idea that the problems are different means DIFF. How did I spell different? Totally wrong. Being the problems are different, order matters. And I'm not going to ask one person to do more than one problem. And the people are separate. And so it fits that definition of a permutation. I have 22 people and I want to pick 3. And so I'm going to ask everybody to, with your own calculator, figure out that 22p3. And what are you getting?
40.
I'm sorry. I think I have to leave now.
Is it? Oh, God. We all have to leave now. Thank you for making me aware of the fact that I've been taking too long. We'll pick up from here next time. If anybody wants to stick around to,
I have a question about the project.
yes,
Because you said we have to interview 20 people with 3
Right.
different questions. Do we have to write their last name?
no,
Because I was interviewing my work, but I didn't know if I had to write all their last names down.
no, you don't have to. Just something, make a list, let me know that there were indeed 20 people there. Okay? Well, I just
Alright.
want to make sure you didn't make up the results. Or if you made up the results, I want to make sure that you had to work hard enough. So, listing it out.
I
All
was
right?
asking all my employees that I work with, like, the questions. I just didn't know when to put them in the Venn diagram, if I had to put their last names too.
No, no. And when you put them in the Venn diagram, you really only need to label the cardinality of the regions. So the only place you need them separate is when you make the list of these were my results.
So you don't have to put the names in the like in the circles.
No, in the circles, all you're putting in is the cardinality, like in the example that's on the handout.
So pretty much just put the names in like below it, like the names.
Yeah, you're just putting the names in the list of when you list your results.
All right. Okay.
All right,
Thank you.
you're welcome. Connor, can I do anything for you? Connor, are you there? Did you have a question? Connor? Connor? Okay, Michaela, I don't know if Connor's there or not. Michaela, you just ran out of time.
Yeah, that was basically it.
Okay. I don't think it would be fair to everybody else in the class to give you another shot at it.
Yeah.
And from the work that you had, it wouldn't be fair to like give you double the time as everybody else.
Mm-hmm.
When you were in high school, did you get extended time in math?
If I didn't have a class right afterwards, they'd let us stay a few more minutes. Or if we wanted to, we could retake it. But like you said, that wouldn't be fair to everyone else, and I wouldn't want to do that to everyone else.
But it wasn't like you had a IEP or something and you were given extended time in high school.
No, most of the time, all they could do was give you like some sort of extra credit project on the side. That was the only other thing that they had suggested to do.
As a rule, I don't like giving extra credit projects because usually if somebody is begging for an extra credit project, it's because they're not doing well. And so in my mind, an extra credit project is something that's harder and more involved. And so if somebody's not doing well with the basic material, to throw something harder at them, I think it's better use of their time to put more effort into the work that they were doing anyways.
Yeah.
But I will tell you that I dropped the lowest test grade.
Okay.
So don't stress about this one. And I will keep time into consideration when I write the other tests. I'll put them in the questions in order. I won't have it randomize the order. Put down, you don't have to rewrite the question or anything. Put down the same amount of work that you have to put down in order to do the homework, right? Because hopefully you're doing the homework pencil and paper. And hopefully it won't be an issue for the rest of the tests. Does that sound okay?
Yeah.
Okay. All right.
All right. Thank you.
I feel horrible, but honestly, that test didn't have any more questions than the pencil and paper tests that I usually give. And usually time is not an issue for people on the set test.
I think it was a little bit different for me because I'm not used to taking tests online. I'm used to the paper, and I didn't have the paper right there. So I had like my computer over here and my paper over here and trying to look back and forth and make sure. It was just a hassle a little bit. I think it was my first test online. So it was just getting used to it, I think.
Okay. All right. Well, we'll write it off to that. And hopefully every other test grade will be a heck of a lot better.
Yeah.
Okay. All right. Okay.
Have a good rest of your day.
You too.
Thank
Bye.
you. Bye.